Hi everyone. Let's look at some probability. First of all, let's talk about what probability is and what that definition is. And so when you're looking at the probability of some event occurring, you're always going to look at the number of successful ways something can happen over the total number of ways that it could happen. All right, this denominator part, this is what we've kind of been working on, the total ways that you can do something. That's when we're using those combinations or permutations to see how many ways something can happen. Now, it's not always that complex. We'll start off with some easier ones, and we'll kind of get to the ones where you have to look at those combinations and permutations. But first of all, understand that when you're doing probability, and you really have a range of values you can end up with for probability. If you think of something that's totally impossible, like you're going to roll a 7 on a die, well, it only goes 1 through 6, so it's not going to happen that you're going to roll a 7. So there would be 0 successes out of a total of 6 possibilities when you roll that die. Okay, well that's just going to reduce to 0. Over here, I have the probability of an event happening that's guaranteed, like rolling a number that's less than 10. Well, it goes 1 through 6, so all of them are less than 10, so that'd be 6 successes out of a total of 6 possibilities, which would reduce to 1. And so what happens then is probability is always going to fall somewhere between 0, and this is like the probability of some event. It's always going to be bigger than 0, but it's going to be less than or equal to 1. So if you ever get a probability of 4.2 or something like that, you know you did something wrong. It has to be between 0 and 1. Let's look at just the old standard marbles in a bag kind of problem. We have a jar, has 2 red marbles, 3 blues, 1 green. What's the probability of drawing? Okay, so to start off with, what's the probability of getting a red marble? So how many successes are there? Well, there's 2 red marbles. Out of a total, there's 6 marbles in the jar. So that would reduce to 1/3 probability. And I would probably, that's a simple enough little fraction. I would just leave it as the fraction. Don't feel like you have to go decimal on that. Okay, next example, a blue or a green marble. Okay, I've got 3 blues, I've got 1 green. That's a total of 4 successes out of 6 marbles in the bag. So that would reduce to 2/3 probability. All right, this next problem, okay, so that's a pretty elementary concept of probability. Let's make a little bit more advanced concept here where you see how many green marbles do I have to add to the jar to make the probability of pulling out a green marble 1/2. Well, it's tempting to immediately jump in there and say 2. I need to add 2 marbles because that would get me 3 green marbles and that would be 3 out of 6. But the problem with that is if I'm going to throw 2 more green marbles in there, I don't have 6 marbles in the jar anymore. I now have 8 marbles, and 3 out of 8 isn't 1/2. Now these numbers are low enough that you might be able to kind of figure them out without, might be able to figure this particular problem out without a whole lot of math involved, and you can just do it in your head. But I'm going to show you kind of how you would do this in case the numbers get larger. Okay, so let's say that you have, right now you have 1 green marble. That would be a success. But you're going to add some more marbles in there. We just don't know how many. And that would be your success over your total, which you currently have 6, but remember you're adding some marbles to the bag. So it would be 6 plus x. That's what you're going to end up with. And you want that probability to equal 1/2. Okay, so if you do your cross products, you end up with 2 plus 2x, just distributing my 2 there, equals 1 times 6 plus x. Okay, so let's get our x's together on one side, our 2's together on the other side, and you end up with x equals 4. So we would need to add 4 green marbles. And then if you added 4, if you think through that, I had 1 to start with, so that's 5 marbles. Okay, and then I had 6 marbles in the bag, but if I add 4 more to it, I'm going to end up with 10. Yep, there's my probability of 1/2, so that would check. Okay, let's look at this type of a problem. We have 100 students that were asked what fruit they chose at lunch. And so there's this table here that shows kind of the results of this survey. So you have to start off and complete the table. Sometimes they're nice and they'll make the table and fill it all in for you. Sometimes they'll give you partial. Sometimes they'll just write it in words and you have to draw out the table, whatever the case may be. All right, so the first thing I guess I'm going to do is remember that they ask 100 students, so that's my grand total here. I have 100 students. 49 of them were girls, so that means 51 of them were boys. Let's see, I could do this. 11 girls liked bananas, 16 boys liked bananas, so that gets me a total of 27 people that said banana. Same thing on the pears. I've got 27 people that like pears. Okay, and then to find out this other part over here, we're going to have to do probably some math on our calculator. So if I've got, let's say, 49 girls here that I surveyed, and I'm just going to subtract out then, you got your 49 minus the 11 banana lovers and minus the 17 pear lovers, gets me 21 girls that liked apples the most. Do the same thing with your boys. 51 minus the 16 minus the 10, that gets us 25, which is a total of 46 students that liked the apples. Okay, so once you have your chart filled in, then you go answer your questions. What is the probability that a banana was chosen? Okay, well, if I look at my table, I have 27 people that liked bananas, so that would be 27 out of 100. Okay, what is the probability that a boy was asked? Okay, so a boy, I look and I said, oh, there were 51 boys, so that would be 51 out of 100. Okay, so that's pretty elementary. Now let's try something a little trickier. What is the probability that an apple was chosen given that you asked a girl? So you're no longer looking at your 100 surveys here that you got back. You're really only looking at the girls' surveys because it was given that you asked a girl. You know that you only ask a girl. So I'm really only looking at these surveys right here. Okay. So given that I'm looking at those surveys, what's the probability an apple was chosen? All right, well, there were 21 apples, but it's not out of 100 anymore because I was only looking at the girls' surveys. It's 21 out of 49. And so that would be the probability that an apple was chosen given that you're only asking girls, okay, or that you're only looking at the girls' surveys. I could spin that around and do that again another way. I could say, given that pear was chosen, what's the probability that it's a boy? Okay, if it was something like that, if it was given that I'm only looking at the pear surveys, then I'd only be looking at these. And then the probability of boy would be 10 out of 27. So pay attention to whether they're talking about the whole survey or just part of it. Okay, dice problems. The probability, there's so many games and even with gambling that probability is involved in, but it has to do with how likely something is to happen, and if it doesn't happen very often, then it's worth more in the game or in the gambling situation. Okay, so let's look at this scenario. I kind of like this chart because it shows you what all the possibilities are. If you're rolling 2 dice, it's tempting to say, oh, there'd be 12 possibilities, but it's not 12. Look at my chart. I've got actually 6 times 6, 6 options for the first one, and 6 options for the second die, and that's actually 36 total possibilities here when I'm doing this. So that's going to be like my denominator. That's the total ways that I could roll 2 dice. Notice that when you're rolling dice, that it's considered different to roll a 2 and then a 1 versus a 1 and then a 2. those are considered different rolls. Sometimes I almost think of it like they're colored dice, and so there's this green one and there's this red one, and so it depends on what's on each one. So keep in mind that those are different situations. All right, so now let's look at some probabilities. The probability that you roll a 7. So one of the things I like about this chart is there's a nice pattern to the numbers, the sum of the dice. Here is a 7, here's a 7, here's a 7, here's a 7, here's a 7, and here's a 7. Those are all my 7s. Okay, I've got 6 possibilities out of 36 total, which reduces to a 1/6 probability. Okay, how about the probability that you get a 3? Okay, so let's try that. In my chart, that would be right here. Oh, no, it wouldn't. Sorry, that's not 3. That's 4. All right, it would be right here is a 3, and here is a 3. So I really only have 2 successes out of 36, which could reduce to 1/18. And you can go decimal on these. Typically, if you go decimal on probability, we'll go 3 decimal places. If it's a pretty simple fraction, I kind of leave it, but if it gets kind of ugly, I like to go decimal with it. Okay, so then the last one is the probability that it is greater than or equal to 10. All right, so on that one, and when I'm looking at my chart, greater than or equal to 10. Well, here are my 10s. But it could be 11. It could also be 12. So I end up with 6 out of 36, or a 1/6 probability of getting something that is greater than or equal to 10. All right, keep that chart handy. That'll probably help you with those problems. When we're looking at the complement of an event, throughout this whole video, you're going to see some terms that I've got in red. These are common probability terms. Complement is one of them. The complement of an event is the opposite of it, and so it's notated with this little prime on the A. So the probability of A not happening is really just equal to 1 minus the probability that it does happen. So for example, if the probability that it's going to rain is a 0.3, then if you want to find the complement of that, the probability that it doesn't rain, you just do 1 minus 0.3. Which is just 0.7. A lot of times we can do that in our head. Other times we'll have to kind of type it in the calculator to see what it is. Depends on how pretty the numbers are. So when we look at what's the probability that it's not a 7, well, we would go back to our previous slide. We saw the probability of getting a 7 was 1/6. And so the probability that we do not get a 7 would simply be 1 minus that probability. So 6/6 minus 1/6 would be 5/6 probability that it's not a 7. Another way to word that would be to get something other than a 3. Well, that's the complement of getting a 3. So that's going to be 1 minus the probability that it was a 3. And remember, that was 2/36 or 1/18. So 18/18 minus 1/18 would get us 17/18 for that probability. Or the complement of greater than or equal to 10 would be the probability that it's less than 10. And so you're just going to do 1 minus, remember that probability was 1/6, so we'd be back at a probability of 5/6 for its complement. Let's look at some problems where we are drawing cards. The probability that you get an ace, let's say. And before we jump right into the card problems, let's make sure that we're all understanding everything there is about cards, and that there are 4 suits. You've got your hearts, you've got your diamonds, you've got your spades, you got your clubs, and you have all 4 of those suits. Now, with those 4 suits, you have numbers, ace all the way to king, and so there are 13 of each one of those. You got an ace, you got a 2, 3, all the way to a king, and that's 13 different numbers in each one of those suits. So that is a total of 52 cards. We don't usually talk about the jokers unless it says something about the jokers. All right, so knowing that then, let's look at some of these probabilities. What's the probability that we get an ace? Well, there are 4 aces. There's 1 in each suit. So 4 successes out of a total of 52 cards. That simplifies to 1/13. Okay, the probability that it's a diamond. Okay, well, there's a lot of diamonds. There's ace through king, so that's 13 different diamonds that are in the deck out of 52 cards, which would reduce to 1/4, which kind of makes sense. A fourth of the cards should be diamonds. And then we have the probability of an ace or a king. All right, well, there's a couple ways to look at that. Probably the quickest, easiest way is you're going to just add up in your head all the aces and kings. And so I've got 4 aces, I've got 4 kings, so I have a total of 8 successes out of 52 cards. And then I can reduce that or go decimal or whatever, but that's what your probability would be. I guess maybe I'll go ahead and reduce. 4 goes into both of those, so that'd be 2/13. Okay, how about an ace or a diamond? Okay, an ace or a diamond, so if I kind of thought up the same thing that I just did, I've got 4 aces, plus I've got 13 diamonds, so that would be 17 out of 52. Except that's not right. Because what happens on this one is when you look at all of your diamonds, here you have sitting here the ace of diamonds. And when you look at all of the aces, you also have that ace of diamonds in that set. And that ace of diamonds got counted both times. When I said that there were 4 aces and I said there were 13 diamonds, the ace of diamonds is in both of those sets. So really, 17 50-seconds is too much. It really should be 16 50-seconds. Now that's probably a simple enough one to do in your head, but that leads us into what we talk about with events being mutually exclusive. Okay, so when you're talking about that, it's the probability anytime you're talking about A or B happening. Anytime you have an or situation, you're looking at this or this happening, you're always going to add those 2 probabilities together. Now, when you're doing that, though, you have to always consider, well, are these 2 events mutually exclusive? Meaning there are no common outcomes. They're totally different events. So here's what we've got. The first example we did was an ace or a king. These are mutually exclusive. There's no overlap. There's no aces that are also kings. And so that's considered mutually exclusive. And so the probability of A or B would simply be the probability of A, let's say that was the ace, plus the probability of B, we'll say those are the kings. And there's my 8 out of 52 that I got. Now, the other situation is if they are not mutually exclusive, like when we had the ace or diamond. These are not 2 totally separate events. They do have some overlap with that ace of diamonds. So when you do that, you still say, okay, the probability of my ace was 4 out of 52, plus the probability of my king was 4 out of 52. But I always have to subtract any overlap that I had, any cards in this case that fell into both of those. And I had 1 card that fell into both of those categories. So I'd subtract that. And so that's where I'm getting my 4 out of 52 plus 4 out of 52 is, oh, I'm sorry. Let me go back here. This was aces. 4 out of 52 is aces. This was supposed to be diamonds. I put the 4 there again, but the diamonds were 13 out of 52. 13 diamonds. Okay, that would get me my 17 minus 1 out of 52 would get me 16 out of 52, which could reduce also. All right, so pay attention on those ors, couple things. Or means add, and then you have to pay attention to whether they're mutually exclusive. All right, likewise, we have situations when we're doing probability of A and B. I want this and this to occur. Anytime we have and, that means multiply. Okay, when you do that, there's a little bit of something that you have to pay attention to, and that's whether or not these 2 events that you want to have happen, whether they're independent or not. That means, does the first one affect the second one at all? We kind of have already dealt with this when we were doing our fundamental counting principle. But like an independent event would be the probability of getting an ace and then a king with replacement. That means you pulled a card, you put it back in the deck, and you pulled another card. So the probability of an ace would be 4 out of 52. And means multiply. I put that card back in there, and now there's 4 successful kings, and there's 52 cards that I'm choosing from. So whatever that equals when you multiply those two together. Okay, if these are not independent, that means whatever happens on the first one affects what's happening on the second one. So this would be an example where that happens. It says find the probability of getting an ace and then a king without replacement. So you start off the same way. I've got 4 aces out in that deck out of 52 cards, and means multiply. But since it's without replacement, I'm keeping the card that I pulled. Well, there's still 4 kings in that deck, but there aren't 52 cards. There's only 51 cards. And so sometimes you'll have to start reducing that total. Sometimes you'll leave it the same if they happen to be independent. So look for that to happen also. Again, remember, and means multiply. Now, we've done some easier ones that you don't have to work too hard to get that total possible. The number of cards is 52. The number of dice possibilities is 36. But sometimes that gets a little trickier, and we're going to have to do permutations and combinations to find out that total number of ways something can happen. And this is a really good problem. You're going to want to star this one. This is going to be on your assignment, probably on your test. Make sure that this one makes sense to you, and go over this a few times if you need to. It says your class is given a list of 20 study problems, from which 8 are going to be put on the test. Okay, now that's kind of nice. The teacher gave you all the study problems to do. The problem is it looks like you only know how to solve 15 of those problems. So find the probability that you'll be able to solve 6 of the 8 problems on the test. All right, so here's what I've got. I've got 20 problems. 15 I can do, so those are, I'll write a yes. Those I can do, which means that there's 5 on that study guide that I do not know how to do. All right, and there's going to be 8 problems on the test. I only want to get 6 of them right. Well, I'd like to get them all right, but in this example, we're just trying to get 6, exactly 6 correct. And so when I look at this, I'm going to set this up as a probability. It's a fraction. In the denominator is going to be the total ways that this test could be created. All right, so on a test, I don't really care the order that the teacher puts those questions on the test. So if order is not important, remember that that's going to be combinations. It's combinations of, there's 20 problems there, and the teacher's going to choose 8 of them to put on the test. So that's the total ways that that test could be made. Now on the top is going to be a success, and a success to me is the 6 of the 8 correct. And you kind of have to do this in parts. You have to first look at a situation with, I've got to get 6 of those that are the ones I know how to do, but then that also means that there's going to be 2 problems that I don't know how to do that I want to fall on that test. All right, so it's going to be combinations because I don't care about the order. There's 15 problems that I know how to do, and I want 6 of those to be on the test. And to force it to stay at 6 that I know how to do and still have 2 that I don't, I've got to also look at the ones I can't do. So there's 5 of those that I don't know how to do, and I need, well, if there's 8 problems and 6 of them I can do, then 2 of them I want on there that I can't do. All right, and then you just type this in your calculator and multiply it all out and see what is that probability that you get exactly 6 right on that test. All right, now that's a nice example. Again, go over that again, listen to that one more time if you need to. That's a pretty common scenario that we look at. The next thing I want to look at is one that's probably more interesting and more likely of what we would do, is the probability that I'm able to solve all of the problems. Okay, so let's look at this. The denominator is still going to be the same. I still have 20 problems. I'm going to pick 8 of them. That's still my denominator, still the total number of ways the test can be made. But if you think about this, now let's set up, here are the ones that I can do. These are going to be the ones I can't do. I know how to do 15 of the problems, and if I'm trying to get all of them correct, then I need 8 of those 15 to end up on the test. And that means of all the ones I can't do, which is 5, I'm going to want none of those on the test. So I do 5, choose 0. And we're multiplying in here because you want this and this to happen. And so you would type that in your calculator, divide it out, see what you get for your probability that you actually ace that test, given that you only knew how to do 15 of the 20. All right. Let's look at some more here. What is the probability that you win the Pick 3 lottery? Okay, now a lot of the time, most of the time in a lottery, it doesn't matter the order that those numbers are picked. You pick your lucky numbers, you bubble them in, you turn that in, and you just hope that those are the numbers that come up. It doesn't have to come in any particular order. But this particular lottery, it's called the Pick 3. You've got to pick 3 digits in the correct order from the numbers 0 through 9. And they don't do any repeating at this. Okay, so you have to think of what's the probability that you will get that correct. All right, I'm going to look at this more. Instead of doing a big fraction, I'm going to do a lot of little fractions. And when you do this probability, a lot of times there's different ways that you could set this up and you'll end up with the same answer. On this one, I'm going to start off and say, okay, what's the probability that I get the first one right? Well, there's only one correct one. I've got to pick the right number. There's one correct lottery number. But how many possibilities are there for that first number? Well, 0 through 9, I'd have 10 options. And I would do it again, and I'd say, okay, what's the probability that I get the second one correct? Okay, well, there's still only one correct one, but since there's no repeating, and I've used up one, I'd only have 9 options for that second number, and on the third one, again, only one correct one, but now there's only 8 options. And then we could multiply those fractions together. Another way you might have looked at that is you could have said, oh, there's only one correct lottery number, and since the order is important on this one, you'd be doing permutations of 10 numbers and you're going to choose 3 of them. This would get you that same answer. Just different ways that you might work through that. On this next problem, we're looking for the probability that you pick 7 winning lottery numbers in any order from the numbers 1 through 40. So typically when you're doing Powerball or any kind of lottery number, it's more like this where the order is not important. However, in the end, there's one winning lottery ticket, and maybe multiple people happen to pick those same numbers, but there's only one winning ticket. So I would only have one success out of a total of, how many different tickets could I come up with? Well, it would be combinations, because the order is not important. There are 40 numbers, and I'm going to pick 7 of them. All right, you type that in your calculator, and that's the probability that you win the lottery. Don't play. It's not a good plan. All right, last one here, and this is from The Price is Right. If you ever watch The Price is Right, they do this thing where they have the price of the car there, and you have to guess what the price of the car is, and if you guess it, then you win it. Okay, so let's look at this. What is the probability that a person wins the car? With nothing here, with no help whatsoever, what would be that probability? Well, we're going to start off and look at, I guess, each one of these. You have 5 digits, and so how many correct answers or numbers are there for this spot right here? Well, there's really just the one, whatever it's supposed to be. If it's a 2 or a 3 or whatever it might be, a 1, there's only one correct one out of, I'm assuming then that there's 10 possibilities, so I'd say 1/10 times, for the second one, well, I'm looking for this spot. There is only one correct answer, so it'd only be 1 out of, and then typically in this game you don't get to repeat numbers. You know, you're just picking numbers randomly, but they don't repeat, and so then you would only have 9 options for the second number. And then you would keep going with that. It would be 1/8, and 1/7, and 1/6. And then you can multiply that all out. Okay, again, you could do that with a permutation of 10 permutations of 6, and that would work as well instead of having to type that all in your calculator. Either way. All right, so let's look at this second question down at the bottom. It says, what if the first number is already known? Okay, so that's a different scenario. So if the first number is already known, well, then the probability that you get it correct better be 1 times the probability you get the next number correct. Well, the rest of that's going to stay the same. It's going to keep reducing because you keep using up numbers. And so you'd end up with this for your probability that you know it if you're given the first number. I think you have some examples on your homework where they give you more than one number, and so then you'd fill in, you know, that one more than one time. All right, that's the end of this probability lesson. Good luck.